My name is Finn, and this is Game On's Lesson 8 on energy. When we talk about energy, we often mean electricity, the secondary energy on which the modern world runs. Electricity is very versatile. We can use electricity from pretty much anywhere to do pretty much anything that needs it. Generating electricity from what we call primary energy sources is more complicated. Choosing which sources to use means making decisions about carbon emissions, reliability, where electricity is required, and what technologies to fund in order to access these new sources. The combination of primary sources that we choose to use is called the energy mix. Sometimes, when we talk about this combination, people like to discuss clean power versus dirty power. All power generation comes at some cost, whether it's gas emissions that amplify the greenhouse effect or biodiversity impacts from flooding or mining. No electricity is truly clean, but many, like fossil fuels, are much dirtier than others. People discussing the energy mix will also compare renewables and non-renewables. Renewable energy sources regenerate faster than we use them up, things like solar, wind, or tidal power. Non-renewables are the opposite. They're used up faster than they can form. This includes oil, natural gas, and nuclear power. Renewable power can still produce unfortunate waste products, like used up solar panels, whilst non-renewables can produce little to no greenhouse gases, like nuclear. We spend so much time discussing the energy mix because there's no single correct solution to our energy needs. The important thing is doing as little damage to the climate as possible, and using what progress we make to support repairs and further progress. Let's look at some of the progress we've already made. Solar power is an important part of a sustainable energy mix. It's a low-cost, renewable power source that produces no direct greenhouse gas emissions. But photovoltaic cells, the technology which makes solar power possible, do have their issues. They're difficult to recycle, and making them currently relies on coal-powered factories in China. In the longer term, there are also areas of the world that don't get enough sun to make solar power a meaningful part of their energy mix. Wind power is another popular renewable. Wind has many of the same benefits of solar power, and similar downsides, with some materials in wind turbines currently being really difficult to recycle. Those turbines can also be dangerous to local wildlife. Romania provides a good example of this problem. Wind farms have to be built in very specific locations, where the wind is strong and reliable. The western coast of the Black Sea is perfect for this. Unfortunately, those winds are also crucial to the Via Pontica migration route. Named after an ancient Roman road that followed a similar path, the winds carry birds and bats through an area of huge wind power potential. Over a 4-year period, researchers recorded thousands of animal deaths linked to Dobruja's wind farms, from impacts with blades to lethal changes in air pressure. Yet the team also found a pretty good solution. By just slightly increasing the speed which would activate the turbines, deaths fell by 78%, while only cutting power generation by 1/3 of 1%. Hydropower is another form of renewable energy. Up to a certain level, hydropower dams can easily adjust how much electricity they generate. Building a dam can be tricky, however. It's impossible in some areas, and damaging to local ecosystems where they are viable. Geothermal energy is another location-dependent power source. The transition to a more sustainable energy mix is often promoted by its job creation effect, and geothermal energy creates more indirect employment than any other power source. Geothermal is also very reliable. Unlike wind or solar, it can generate power regardless of the weather. And beneath the crust, the Earth is extremely hot. Geothermal power has the potential to produce huge amounts of electricity. Biofuels are a complicated one. As biofuels turn organic matter into substances like ethanol, some sources are renewable and others are not. Their carbon emissions vary, with older types like corn ethanol releasing large amounts of CO2 and so-called second and third generation biofuels releasing less than traditional fossil fuels. Biofuels use large amounts of water and land, and in cases like corn ethanol are made from edible material. This means that production directly constrains food supplies. Nuclear power is even more complicated. Except for small amounts of water vapor, nuclear plants produce no greenhouse gases. And while nuclear fuel is non-renewable, supplies on the Earth's crust are expected to last for decades to come. Nuclear energy's downsides are well known. Nuclear waste emits ionizing radiation, microscopic particles that cause mutations and cell death in living creatures, including humans. Nuclear plants create electricity through heating water, which means a large and reliable supply, preferably on a river or ocean. This limits where plants can be built, and it also increases the risk of pollution. And uranium, as we just touched on, is still found in the Earth's crust. It has to be mined, at significant cost to local biodiversity and environmental quality. Then there are fossil fuels. Fossil fuels are hydrocarbons, chains of hydrogen and carbon atoms that form from dead organisms, pressure and heat in the Earth's crust. They're low cost, versatile, and easily exploited. As a result, they were some of the earliest power sources developed during the Industrial Revolution. Fossil fuels are also highly polluting. Research attributes as many as 3.6 million deaths per year to our usage of them. They are central to the climate crisis, the increasing greenhouse effect, and the threat of human extinction. They are the largest source of electricity in the energy mix. The energy mix is itself the largest producer of greenhouse gases, with agricultural and industrial emissions in a distant second and third place. But this is only half the story of our carbon emissions. Most processes are a combination of multiple activities. The food system, the process of supplying food from field to table, creates around 26% of our global emissions. Day-to-day life, like buying products, travelling for work and leisure, heating a building and powering its appliances, is another complicated mix of emissions. Coincidentally, in the EU, this is responsible for 26% of energy use. International comparisons can be tricky. Global emissions are extremely uneven, with 2/3 of emissions coming from the 10 most emitting countries, and China, top of the list, produces nearly double the greenhouse gases of second place, which is the United States. Yet China is also a much larger country than the United States. Measuring per capita, or per person, Chinese greenhouse gas emissions drop from first in the world to 35th. Many European countries are more polluting per capita. Poland, Germany, and the Czech Republic are 9, 10, and 14 places higher than China, respectively. So what does all this mean? It means that we need to make big changes to where our electricity comes from. This is one of the ideas behind net zero. Net zero is the point at which the amount of greenhouse gases we're removing from the atmosphere equal the amount we're releasing into it. The European Union is aiming to reach net zero across all member countries by 2050. Without net zero, the greenhouse effect will become too intense to support life as we know it. Average global temperatures are rising. If they increase above 1.5 degrees Celsius compared to pre-industrial levels, humanity faces numerous crises. Food and water insecurity, extreme weather events, mass extinctions, and increased mortality will be inevitable. Industrialization and its consequences have made net zero a big challenge. Industrialization has shaped the modern economy, as we'll discuss in future lessons, and ravaged the environment. The Industrial Revolution, which began in Britain around 1760, is generally understood as the beginning of human influence on the climate. This is the reason that we use pre-industrial levels of greenhouse gases to measure the scale of the climate crisis. One thing is certain, without big changes to the energy mix, net zero will be impossible, and those big changes will require new investment, ideas, and technologies. Take carbon capture and carbon offsetting. Extracting carbon from fuels before they are used, or from the waste products their usage leaves behind, separates that carbon from the atmosphere's greenhouse effect. Offsetting takes a different approach. So-called carbon credits act like a tax on emissions, forcing polluting firms to match their carbon footprint through investment in carbon reduction projects. And how do we make renewables more efficient? Renewable energy isn't always available, in the same way that a mound of coal is always ready to be burned. This means that energy needs to be stored once generated in a way that it can easily be accessed later. Algae biofuels are another promising technology. If water usage and scale problems can be solved, algae offers a high-energy, low-carbon fuel source, which can be easily grown without using up edible food stocks. Renewables also face difficulties in transmission and distribution, known as T&D. The closer electricity can be produced to where it's needed, the lower the amount that is lost as heat and radiation through wires. Miniature wind turbines and solar panels can provide power to extremely isolated places, which might otherwise be forced to use local fossil fuel generators or other sources of power. We talked earlier about the pros and cons of nuclear power. A new type of nuclear reactor, which uses the element thorium instead of uranium, could revolutionize this part of the energy mix. Thorium is easier to find and more efficient per ton than uranium. Its waste is also less dangerous and harder to weaponize, which could make it safer to share around the world. One of the biggest innovations towards net zero is more of a concept than a technology. It's often called Industry 4.0, or the Fourth Industrial Revolution. The invention of the steam engine in the 1700s began the first industrial revolution, with electricity and then computers ushering in further progress. Now, large-scale data collection and automation is making another round of innovations possible. Complex data analysis and the use of artificial intelligence can give us a better understanding of huge parts of our world, from the damage we are doing to the climate to more efficient ways to make products and grow food. New data and computing technologies could be the key to thorium reactors, algae biofuels, and all kinds of clever energy storage solutions. If we can use computers to address these problems, and not just prop up industries which are destroying our climate, we might aspire to even bigger goals than net zero. But none of these opportunities will make a difference without changes to our lifestyles. You can start making a difference today, just by changing small parts of your routine. Turn off lights when you're not using them, or try walking next time you want to visit somewhere. You can also dig deeper into things like home insulation or renewable energy suppliers. You might be surprised how much carbon your lifestyle produces. To find out more about things you can do to help and understand the impacts of your decisions, you can also download the Game On Climate Game app for smartphones. By answering a few questions about day-to-day activities, you can learn how best to contribute in the fight against climate change. 2050 is not as far away as it sounds, and net zero will not be possible without everyone working together.